Với lại tụi em record lại và sau đó sẽ upload lên YouTube, có được không anh?
Ok, ok.
Dạ.
À,
Rồi. Chào mừng mọi người đã quay trở lại với buổi guest lecture thứ hai của khóa học Math Modeling của PiMA. Thì hôm nay chúng ta có tiến sĩ Văn Phụng Trường Sơn có give một cái bài talk về chủ đề Facets of Randomness. Thì sơ lược một chút về anh Sơn. Hiện nay anh Sơn đang là nhà toán học ở Đại học Fulbright Việt Nam, và trước đó anh làm sau tiến sĩ ở trường University of Pennsylvania ở Hoa Kỳ, và trước đó nữa thì anh là làm PhD ở trường CMU cũng ở Hoa Kỳ. Thì anh Sơn rất là hứng thú với những cái lý thuyết phương trình đạo hàm riêng và lý thuyết ngẫu nhiên, cũng như là muốn biến những cái hiện tượng trong cuộc sống trở thành những cái kết quả định lý toán học. Thì mình cũng biết anh Sơn một thời gian và thấy được cái đam mê với toán học cũng như là đam mê phát triển toán học ở Việt Nam của anh. Và hôm nay mình cũng rất là vui được cùng mọi người nghe cái bài giảng thú vị của anh. Xin mời anh Sơn.
ok, cảm ơn Trung. Từ từ mình đang cố gắng share screen mà không biết tự nhiên nó bị nó có vấn đề, đợi mình chút nha. À,
Dạ, anh Sơn. Thì trong quá trình bài giảng, mọi người cũng có thể đặt câu hỏi trong chat, và tụi mình cùng những cái mentors khác sẽ cố gắng tổng hợp thành những câu hỏi để lúc sau anh Sơn có thể trả lời được, hoặc là trong lúc ảnh đang nói luôn nếu như mà liên quan trực tiếp.
rồi cái technical problem. Ok, hy vọng là bây giờ ok, mọi người có thấy cái này của mình không? Screen của mình.
Được, thấy ra.
Bây giờ, tại vì hôm nay là mình dùng OBS để cho nó tiện việc gọi là switch, đổi cái screen của mình á, cho nên là nó sẽ hơi bị lấn cấn một chút. À, xin lỗi các bạn.
Anh có livestream toán nhiều không ạ? OBS để
Hồi,
để
hồi
Trung
trước hồi
switch
trước
nha.
thì có hồi trước có livestream cho các bạn học ở bên Mỹ.
Ồ.
Nhưng mà sau thì không nữa, tại vì hồi đó là Covid.
Dạ.
Ok, các bạn thấy rồi đúng không?
Dạ.
Rồi, bây giờ mình xin phép là mình nói bằng tiếng Anh nha, tại vì là mình học à, undergrad với lại grad school ở bên Mỹ, cho nên là cái vốn từ vựng về toán ở tiếng Việt thì nó không được tốt cho lắm. Cho nên là chuyện này tiếng Anh, có gì các bạn hỏi, nếu các bạn hỏi thì các bạn cứ hỏi tiếng Việt, thì mình cố gắng trả lời bằng tiếng Việt. Ok. Mình cũng xin là các bạn nếu mà có thể thì bật màn hình lên, tại vì là lúc mà à, give talk thì nhìn vào cái màn hình thấy mặt các bạn thì nó vui hơn, giống như là mình đi dạy thật, nếu các bạn có thể, không bắt buộc. Okay. So today I'll be talking about facets of randomness, right? Thanks Chung and PiMA for their works, right? I've been following the works of Chung and the foundation since a long time ago, and it's been very meaningful. All right, so let's get to it. So today I'll be talking about randomness, which might be something that in high school you encounter sometimes, but not many, right? Not much. And sometimes students are left puzzled by randomness, and randomness seems scary. That happened to me when I was a student in high school. So I want to to talk about it so that you might be more familiar with it, right? And perhaps later enjoy working with randomness. Okay. So here's the outline of today's talk. First, I will talk about what it is, randomness. And the next part will be devoted to how you can see beauty in randomness. Right. Feel free to ask me questions. All right, so let's get to the first part. So I would like to invite you to think about this very, very simple phenomenon that you encounter perhaps every day in your life. So the question is, you flip a coin, what do you expect will land on the top after one time? So feel free to type your answer in the chat. So this is a little bit more interactive. Head and tail, a face. Okay. Okay, so the answer is you don't know, right? You don't really know. If the event hasn't happened, you don't know, right? So you only can tell that, right, either head or tail is up, right? Sấp hoặc ngửa, right? Not head and tail, right? Head and tail logically is not the same with head or tail, okay? So this is the first lesson. Head and tail, right? It's not the same with head or tail. Okay. Why is this? That will be a logic lesson, right? So if you are interested in logic, perhaps you can read more or vote for having a course in logic. Maybe PiMA will sponsor one. I don't know. Okay. So the first answer is you don't know. All right. How about this question? What do you expect to land on the top after the 11th time? So I'm expecting answers. All right, you still don't know. That's the right answer. All right. And what's about this one? What do you expect for the number of times the coin lands on head after 10 times? So how many times do you think the coin will have a head after 10 times of flipping? So you don't know. What do you expect from your at least 5 times? Yes, 2, 5. Okay, so that's right. You actually don't know, right? If I ask you this question, you don't really know. But if you do some experiments, right, you will see sometimes it's 2, sometimes it's 5, sometimes it's 6, right? So actually, let's do a experiment, okay? I have here my screen. All right. So I'm gonna, this is a program called Julia. All right. So I wrote some program, coin. Okay, so this program will flip the coin for me. All right, can you see this? All right, I want you to record this. Okay. So this is the first time. Heads. Okay. Heads. I'm gonna type in heads. The second time. Heads. Still head. The third time. Okay, I'm gonna do it 10 times. Okay. 3 times head. Okay, 3 out of 4. 3 out of 5. 3 out of 6. 3 out of 7. 4 out of 8. 4, no, 4 out of 9, right? 4 out of 10. Okay, so I have 4 out of 10. Okay, all right, let's get back to my thing. Okay. Okay, so after the first try, I know this much. Okay, so if I repeat this process again 10 more times, what do you think? What should be your guess for the next time if I flip the coin 10 times? Well, you don't know, but can you have a guess? Right? So Thiên Long, right, say that maybe 4, maybe 3. Okay. Okay, second time. Maybe 4, maybe okay. Maybe 4, maybe 3, right? Maybe 5, right? If I repeat this process 100 times, right, what do you think will happen? So if I repeat this process, okay, repeat the process 100 times, okay. I mean 100 of 10 times, so 1,000 times, I guess. Okay. Okay. What do you think will happen? How many times you think will have a head? Maybe 200 or 300? Any other guess? Maybe around 500. Okay. All right. So the answer should be, it's gonna be closer to 500 than to 200. Okay. And if you keep repeating this process, maybe 1,000,000 times, it's gonna be close to 5 million. No, 500,000. Okay. So given that you have a fair coin, okay. So given you have a fair coin, that means, okay, the chance to land on top on head, right, is the same with the chance to land on tail. So that means if you keep repeating, yes, this is a law of large number. That's right. Okay, somebody, so Thing Long know what's happening. All right. So that means, right, if the physical property of the coin is so that the head and the tail would be the same, you would have the same chance to get a head or get a tail. Okay, so that's what it called. That's what's called a fair coin. All right. So you already discovered something over here, right? A fair coin. We're gonna go to okay. Let me not discuss that for now. Okay. So let me go to the first definition, the first concept that we just learned from just that very, very simple example. That is the concept of probability. Okay. So probability is the frequency of some event to happen, given some background knowledge. Okay. So in the previous example, if you flip the coin, okay, 1,000 times, all right, the frequency of heads is going to be the number of times, right? Number of time, the number of time that heads appear. Okay, given 1,000 times. All right. So frequency is something that you learn maybe in high school, maybe in middle school, right? Is that you keep repeating the same process, right? And you count how many times something happened. Okay, that's the frequency of heads. If you want to know the frequency of tail, then you would do the same thing. You would count how many times tails appear. Okay, so that's the first concept. So once you learn this, okay, I'll give you 10 EXP, right? If you play games. The second concept is called a random variable. A random variable is a function that take your outcome and then give you a number. So in our example, we have two outcomes, head or tail. All right. So you can make up many kinds of random variables. Okay. So you could just have a function, okay, that take these two. Okay, let me change my notation here. That takes maybe tail to go to 1 or head to go to 2. This is a random variable. Or you could do something like, okay, right, 1,000, right, or maybe 2,000. Nobody stops you from doing this. However, the most useful thing, way to think about this would be to map the tail to -1 and the head to 1. Okay. So depending on your problem, you would like to model what kind of number it gives. And for what to come, I'm gonna map tail to -1 and head to 1. Okay, so that's only your two outcomes for now. Okay. Okay. So the goal of this is to do math, right? And then here's my example I just talked about. A random variable is a function that for each input, you have a number of output, okay? Any questions so far? All right. Okay, so you gain 10 experience point. Okay, yep, Thiên Long.
Dạ, cho em bật mic nói kìa.
Ok.
Cho em nói bằng tiếng Việt chứ em không có giỏi tiếng Anh lắm. Thì
Dạ.
nãy như anh nói đó là cái hàm cái biến ngẫu nhiên này là một cái hàm số, ví dụ như trong cái này anh đang nói là ví dụ cái mặt sóc với mặt ngựa là anh có thể gán nó thành một cái con số nào bất kỳ, rồi sau đó anh
Dạ.
nói rằng là cách tốt nhất đó là mình cho nó là 1 với trừ 1. Thế vì sao mình lại chọn hai con số đó mà không phải là hai con số khác đó?
Ok, cách tốt nhất cho cái ví dụ mình sẽ làm trong cái bài này. Ok, tùy vào bài toán mà bạn muốn làm thì con số bạn chọn nó sẽ khác nhau. Trừ 1 với 1 nó chỉ tốt nhất cho cái talk của mình hôm nay thôi.
Rồi, rồi.
Ok. Ok. Có bạn nào có câu hỏi nữa không? Okay. So I'll be honest, like giving this talk, I'm more scared than giving a lecture to my students because I don't know what your experience would be, right? Okay, so the next concept would be expectation or average. So this kind of thing is something that you learn, right? You know, in your daily life. So the expectation of a random variable is just the summation, okay, of the probability that the event would happen. So remember, this is a frequency, okay, of some event. Okay. I guess with my definition of frequency up here, right? Frequency is the number of time I would have to divide by the number of trial, okay, of coin flips. Okay, so you just take the ratio of how many times head appear and then divide it by the total number of coin flips. That gives you a probability. And then, of course, you would like to repeat the process here as many times to get the correct probability. So, like you say, that's a law of large number. And then, okay, so the way I'm writing it now is a little bit different from what the theory would tell you. Okay. I mean, standard textbook theory would present it differently for me, but I just want to make this consistent with my talk. Okay, so then you multiply this with the outcome. Okay, with the number of that outcome associated by the random variable that I talk about. Okay, so that gives you the expectation. And for example, right, in our coin flip, right? So if we have fair coin, right, then the probability for the head would be 1/2, right? And then the probability for the tail would be 1/2. And then because I use my random variable so that the head would give me 1 and the tail would give me -1, right? Then my expectation using this formula would be 1/2 times 1, which would be the head, right? Plus 1/2 times -1, which would be the tail, which is going to be 0. Okay. Of course, if you choose different function for your random variable, it's going to be the average value between the two random variable, between the two numbers. Okay, so this would be the two main concepts that I would be using. All right. So maybe you already know this, maybe you haven't known this. I would encourage you to maybe try to explore more about this if you are interested after this talk. Okay. So let's do something. So you all know this guy, right? Albert Einstein. What he likes to do, what people claim that he likes to do, is to do something called a thought experiment. Okay. Okay. So, okay, so you all know Vlog, right? Okay. So I can only get the info from yesterday, because I made the slide yesterday. Okay, so this is the winning number for yesterday. All right. Okay, so let's try to think about Vlog. So suppose you have you know that the probability for winning a jackpot, right, with Vlog is 1 in a billion. So 1 over 1 billion. Okay. So the probability of winning. So if you would like, you can write it as minus a 10 to the minus 9, right? So this is 1 over a billion. All right. So if you lose, it's just like a typical day, right? So typical. You don't really care, right? A lot of people buy Vlog, right, and don't really care. They don't even check. They don't even check the numbers. So it's like, you know, a typical day. If you win, right, you'll be very happy. Right, very happy. Okay. So this is kind of weird. Or is it weird that you react this way, right? So here's an observation. So suppose, right? Suppose every decision that you want to make depends on either flipping a coin or winning big lot, right? Which one do you think would be more stable? Which life do you think would be more stable? So I claim that your life is more stable if you depend your action on winning big lot or not, compared to the action that you use, that you base on the coin flip. Okay. Okay, so so you can unmute yourself and discuss. Okay. I like to have discussions.
I think for the coin, if we depend the life on the coin, probability is more stable than the probability to win the with lot, because the probability of the coin is much higher than the probability of the with lot.
Okay, so that's mine, right? Okay.
Yes.
Em cũng đồng ý với bạn đó. kiểu gieo đồng xu lên thì 50-50 hơn, chứ còn cái việc lót thì chắc chắn mình xui rồi, thì quyết định mà dựa trên cái việc lót thì chắc chắn là thôi mình quyết định cái hướng ngược lại đó.
Okay. Okay.
But if we have someone working in the Vietnam, that's different.
Wow. Okay. Okay. Any other opinions? I want to know your reasons.
I think Vietlot is not just head and tail, because it, like, the person who wins the prize needs to have the correct array of numbers. So the array numbers not just include 2 numbers, but it's more, and it's not like a binary anymore.
It is not binary. Well, it's still binary. It's still winning or not winning or losing. In that sense, it's still binary. But you are getting somewhere. Okay.
Yeah.
Any other opinions?
Em nghĩ như thế này, thì cái kỳ vọng, nếu mà mình so sánh mình tính cái kỳ vọng của việc mình trúng việc lót thì nó sẽ là một số âm, còn nếu mà mình là cái kỳ vọng của cái việc tốt score này thì nó là một số không, thì em nghĩ là nó ổn định hơn.
Okay. Okay. So let's think about this together. Okay. So let's rephrase this thing. All right. Let's have a live scenario where you would, so first, right? So first scenario, and then the second scenario. Okay. So imagine you're like a movie director, all right? So you would like your actor and actress to act like this. So the first scenario is to use a coin toss. And the second scenario is to use big lot. Okay. So the first decision. So decision. Number 1. Okay. So the boy, right? Boy ask the girl, right, to marry him. Okay. And in the first scenario, the girl would use a coin toss to decide. So it's 50-50 chance. Okay. So either marry, not marry. Okay. So that's a big decision in your life. You could, you could base your decision using the coin toss. And if you get ahead, you have to marry. If you don't get ahead, you can still not marry. Okay. And the scenario is that the girl is not that interested in the boy. Okay, so you can see that the chance for the girl to get married is much higher than in the coin toss versus big lot, right? 50% versus 1/10⁹, right? Right. And then the second decision the girl want to make is that whether she should go to college or not. Okay. Maybe this is not a bad. This is a bad example. Okay. Okay. Maybe the example should be whether she want to drop out or not. Okay. Okay, if you flip the coin, then 50% chance you're gonna stay in school and 50% chance you're gonna get out of school. All right. And if you base on your decision on weak lot, right, much higher chance you choose to stay in school, not drop out, right? Because not winning means not saying no. So you can see that, right? If you base your decision on weak lot, most of your answer will be no. Would be no, right? And if you base your decision on the coin toss, right, your life is like more up and down. Right? For the second scenario, you only go down. For the first scenario, you always up or down, like a roller coaster. So if I were to ask you to choose again, which one would be more stable?
I think that depends on the situation.
Okay. Like what?
Like your goal, like if you want the out, like the more stable on the outcome, no, for example, then the Vlog is more stable.
Okay. Right. Okay. So you get the correct idea, right? So it is stable in the sense that it is harder for you to change your answer, right? There is still 1 in a billion chance that you will say yes, but that's very low. You don't really expect it. And of course, right, if you were to flip the coin, you constantly changing your yes or no. So with this observation, with this framework, I would say that your life is more stable, right? If you base all your decisions on weak lot. So I hope I convinced you with this. Okay. Of course, philosophically, right? People would think that unstable means only go down, right? Some people think like that. Okay. But we are not talking about that, right? Sometimes only going down is more stable because that's what you expect. Okay. You don't expect to change outcome too much. All right. So that's a little bit philosophical. So the whole point that I want to get at is that there is, so the coin flip, right, in some sense is more random than weak lot. You change your mind a lot more with the weak lot, with a coin toss, right? So this is something to remember. Okay. So here comes the second guy that I want you to know. His name is Klaus Shannon. He is called the father of information theory. Okay. Why is it? Because perhaps he would be the first person to think about how to transmit information the most effectively. And from his work, right, there will be the notion of, more or less random, consistent with what we just discussed. Okay. Oh, okay. So there's a comment in the chat. Take the decision for taking shower. Okay. Find task by tomorrow. Okay. Yep. Okay. So Google Pixel. Okay. This is what what I was getting at. Stable means the repeatability of the action. Very good. Okay. So what did he do? In 1948, he published this work. This is a paper, or maybe a short book, right? It's called A Mathematical Theory of Communications, in which he wanted to study the fundamental problem of communication, which is that reproducing at one point either exactly or approximately a message at some other point. In other words, so you want to send a message, right, to you, right? It goes to your friend, right? And you want to make sure that this friend can read your message. That's what he cared about. All right. Seems not much to discuss about, right? Sometimes you just put the message into an envelope and just send it out. But things get trickier if you think about an digital, right? If you think about signal, like how computer work, right? The entire the entire world these days, right? Base their technology on just zeros and ones. And how do you know that those zeros and ones would be representing the things you want to say to the other person, right? So from this work comes the entire industry of, telecommunication, encryption, compression, and so on, right? So I would say this is one of the most important work in the 20th century. So, and the bonus is that you only need calculus to understand. It's quite understandable. He is a good writer, and I encourage you to read this. Okay. Okay, in this work, Shannon introduced something called a Shannon entropy. Okay, he didn't call it Shannon entropy, of course, but later on people call it Shannon entropy, which would be the following. So if you have some probability, right? Say coin flip, one half head, one half tail. The entropy of the probability will be the minus of the sum of each probability times the log of its own. You do all this for each probability and you sum it up and you put a minus in front of it. Okay, seems random. Okay, talk about randomness. This sounds really random. Okay, but it's not random because it can capture what we want. So let's think about this. So I want you to do the following. Okay, so here's the question. Compute the Shannon entropy of two examples that we did before. The coin flip, okay. The probability of coin flip. And the second one is the probability of việc lót. Okay, I'll give you 30 seconds. Then I move on to the next slide. You have some formula, all right? And okay, some person say 1 bit, nearly 0 bit. Okay, we haven't discussed about bit. All right. We don't talk about units here. But yes, that will be 1 bit and nearly 0 bit. Each coin is okay. Okay, so let's move on to the next slide. So if you have computed it, here is the computation you can compare. Okay, so it's important that we have a fair coin over here. Okay, so now depending on the kind of log you want to take, it will be a different answer. So in this computation, I'm going to take log base 2. Okay. If log is log base 2, then let's do it. So you have the probability of fair coin will be 1/2, right? Times the log of itself. And then you have the probability of tail, right? Which is 1/2 times the log of itself. So you would have minus log of 1/2. Well, but this is log base 2, so it's just 1. All right. So the second one, again, so the probability of winning will be 10 to the minus 9. You want to times the log of itself. And then you want to compute the probability of losing, which is going to be 1 minus 10 to the minus 9. And then you times with the log of itself. Turns out this is a number. And it's close to 0. Okay. And in the comment, right, Fang, right, he say the unit of this is bit. Okay. Whatever it is, it has a unit of bit. Maybe a joke is that a little bit, right? This one is very a little bit. Okay. Okay, I promise this joke will sound more funny if we are in person, but we're not in person. So yeah. I guess we have to suffer with fake jokes. Okay. Okay, so is this consistent what we discussed earlier, right? So earlier, a fair coin, we say is more random than việc lót because it creates more unstable situation, not repeatable actions. And then you see that the entropy of the fair coin will be bigger than the entropy of việc lot. Okay, so there's some correlation, similarity here, right? So more corresponds to bigger, right? And I guess people would take the same point of view. Most people who work in information theory would think that a probability that have higher entropy would be more random than a probability with low entropy. Okay, so more entropy means more chaotic. More entropy is more chaotic. Okay. Okay, so this is what I want to get over for maybe the first part. Okay, so if you want to remember something from this talk, this is something that you can remember. And later on, this notion of entropy is related closely to the entropy in physics. Okay, I don't want to discuss about this, but when Shannon came up with this function, he talked to von Neumann, and von Neumann say, okay, why don't you use entropy because it describes something similar in physics. So von Neumann, okay. Another name that you want to know if you want to learn about computer science or anything about math. He's a really, really good mathematician. All right. So it turns out that the fair coin is the most random thing among the things that have two outcomes. Okay, this is a theorem. I won't prove it, but that's a theorem. Okay. So within our discussion, I want you to remember fair coins. Okay. It's really random. Okay. Even more random than a coin with probability of head to be 1/3 and the probability of tail to be 2/3. Okay. Can somebody give me some intuitive explanation for this? Why do I say the fair coin is more random than some kind of other coin with probably 1/3 and 2/3? Just to check if you understand what we have been discussing. You can predict the results more easily. Okay. In what sense? Okay, that's right. So yeah, so you have some bias, right? It's easier to predict in what way you're going. So, right, with the bias coin, say, okay, this is called a bias coin. Bias coin, right? In particular, if you have probability 1/3 going up, going head, and 2/3 going tail, right? You are more likely to go with tail, right? So if you base your decision on head or tail, you are more likely to say no. Okay, so you are more predictable. All right. So let's keep in mind, fair coin is really random. Okay, so that's the thing about the first part. I just introduced you about randomness. Okay, so next. Oh, it's 8 p.m. already. Okay. I think I need to speed up. So I want to talk about beauty from randomness. Okay. We learn about randomness, now we learn about the beauty. So I think you learn about differential equations in this course. Right? Did you learn differential equation? Not really. I mean, I thought Chung discussed about it, right? Okay.
Các bạn thì có học mô hình SIR và dạng dân là kiểu dạng difference equations của differential equations.
Okay,
tức là phương
difference.
pháp Euler để approximate.
Okay. So it's the same idea. All right. So instead of so instead of having d over dt here, you can just think about this as u of t plus ti plus 1. All right. Okay. Tn plus 1 minus u of n over here. That's the difference equation. And this one will be v of n plus 1 minus vn. And all of this over here will be un vn on the right hand side. Okay, that's it. Okay, so this is how you translate from differential equation to difference equation. Whenever you see d over dt, you replace it with a difference in time, in a step, right? And then on the right hand side will be something that is the previous step. All right. So okay, I apologize if this doesn't make much sense, but you can translate this into difference equation. The point is that there's a dynamical picture that's going on. You can use the past to update for the future. That's the point. And then here, the C and the K would be just some constant. You can think of that as maybe, 1.1, 0.1, or maybe 0.2 or something like this. Okay, just some constant. And when I talk about equilibrium, okay, I mean there will be no change in time. So that means un plus 1 minus un will be 0. So this is equilibrium. Okay. And a solution of equation that reach an equilibrium just means that whenever you try to update, you don't update anymore. So that means your next update, u sub n plus 1 is going to be the same with u sub n. That's it. And when that happens, something magical appears. When that happens, then this thing is going to be 0. This thing is going to be 0. You're going to have a system of equation. Let me erase all these things so it's clearer for you to look at. You have a system of equation where this is 0 and this is 0. You have 2 equations and 2 unknowns. You can solve for the solution. And one of the solution is 0, 1. And I call it stable because wherever you start initially, right? So in your difference equation, you learn that you have an initial state. U0 to be something, right? Stable equilibrium just means that when you start your initial condition in the domain, right, in wherever, maybe close enough to this point, it's gonna just keep updating and updating until your solution reach that point. Okay. Okay. So perhaps this could be a little bit abstract. I understand. However, if you understand this, it'd be great. Oh, I guess SRI, right? SRI, SIR model. You have some steady states of, you know, sick people in what is it? S is safe, right? Infectious and recover. Okay. So there will be an equilibrium system. SIR is more complicated because it has 3 equations. This thing only has 2. Okay. So if you have this system, then you expect some dynamics. So let me actually run some simulation. Okay, screen. So I have include, right? 0. Okay, so this system is called a Gray-Scott equation for people who want to know the name of this. Okay. So here is a simulation that I want to run. Okay. Perhaps this is a little bit different from what you know about SIR, but let me explain. I assume, okay, so this is a model for chemical reaction. So you can think of the chemicals are kind of, okay, for each of them it's kind of well mixed over here and over here, well mixed. Of course, in the boundary, it's not well mixed. Okay, so here you have some sort of density. All right, density of some chemical, and this is density of some other chemical. First, you kind of separate them out. And you assume that, so this is space, okay, spatial. So over the space, right, maybe on the disk, on the plate, there is some density, and the density of the V, right? So your equation, the equation here, let's look at this. We have 2 things, U and V, okay? This plot that I'm having over here just describe the density of V. Okay, so when V is purple, that means U is green, because purple just means 0, right? And green just means 1. So when there's no U, there's gonna be V. Okay, and vice versa. When there's no V, there's gonna be U. So here, V over here is gonna be 0, no density at all. And most of the chemical V is concentrated here. Okay, so I'm gonna run this video. Simulate live. Oh, okay, let me do it again. Okay, right there. Okay, can you see that? All right, let me do it again. Remove this. First, I have initial condition. So imagine everywhere in space on the top, right, will be no V, and most V concentrate here. And then I run this simulation. It reached an equilibrium where the V dies out. That means there's no more density. Okay, so that means this is all purple. So this is what you would expect when you just have the kind of model that you see using the SIR kind of model. This is what I call ordinary differential equation, ODE, okay? Where ODE or ordinary differential equations is when you just update your solutions with one variable. In this case, it's time variable. You want to see the density evolving over time. Okay. So that's the first concept. Okay, so because time is short, I won't talk about all these things. But I want to say, when you introduce randomness, okay, when you introduce randomness using the coin flip that we discussed earlier, we would get to something called a Brownian motion. Okay. A Brownian motion is just a coin flip that it's just a coin flip that scaling in some sense. Okay. We can discuss about this after the talk, but I want to speed up. So once we have the Brownian motion, we can update the equation to something like this. Okay. So the Brownian motion gives you more terms over here. For those who don't know, this is called a Laplacian. So del of u is going to be partial x squared of u plus partial y squared of u. So this is the derivative in space in the x direction 2 times. This is the derivative in the y direction 2 times. Okay, if you don't know this, it's okay, right? I just want to know that the effect of the randomness come into this thing. Okay, and let's see what it creates. Let's go back to my screen again. All right. So now I will run the full grayscale. Okay, here's my initial condition, similar to what we have done before. But I'm gonna run this. Okay, actually, I'm gonna run this. Okay, first, you see that it looks like it goes to 0 for the density of V, but not quite. Some spots remain, and it's there, and you can see that it's dividing. All right, and if you wait for a little bit more, these things keep dividing, and it keeps dividing. Okay, so what I want to say is that when you have randomness, life becomes more interesting. Like this. Before randomness, your equation just tell you, okay, you kind of die out. You don't have any more density, right? The chemical V doesn't have any more density after reacting with U. But now, because of randomness, V can survive and is creating some pattern over here that looks beautiful. And this is being run in real time. Okay, so randomness, I can claim, wait, this is my personal point of view, that randomness creates beauty in the world. And you should learn more about randomness. All right. Let's get back to my slide here. Okay, so you see some effects. And this effect was found by Alan Turing. Okay. Alan Turing was known more for his work in computer science. So maybe father of the computers or something like that, right? But he has other works that are very, very interesting, especially this one, Turing pattern. He first found this pattern playing with the differential equations, right? Putting more the PDE in, partial differential equations. So that this kind of pattern that you just saw over here can represent nature. Okay, you see that the skin of this cheetah, right, or the skin of this fish, have the spots like what we just simulated, and this all come from the randomness. All right, and of course there are many more things that you can learn about randomness that can make life beautiful. And I think that's the end of my talk. Thanks for listening. I guess the message is that you should go and study randomness, and you will learn more about these things.
Có một câu hỏi in the chat.
Ok, ok, giờ mình nói tiếng Việt nha. Quyết định dựa trên xổ số ổn định hơn. Tại vì lúc này em cũng nói là không, thì nó là ổn định hơn. Về cái nghĩa đó là cái quyết định của em luôn luôn là không. Tỷ lệ cao sẽ là không, thì nó sẽ ổn định hơn lúc mà tung đồng xu. Tại vì lúc đồng xu là bây giờ thì là có, hôm sau thì là không, đúng không? Có không, có không, có. Nó up and down nhiều hơn. Về mặt nghĩa đó thì nó sẽ là không ổn định bằng. Okay, go back to the differential equation. Yes, partial differential equation. Okay.
Em muốn hỏi ở đây là cái hạng tử Laplace của U với Laplace của V nó có ý nghĩa gì về kiểu khuếch tán hay này nọ? Tại vì em thấy trong cái mô phỏng thì kiểu có những cái đống hợp chất đó, sau một thời gian cái nó tách ra.
Đúng.
Thì em nghĩ là do hiện tượng truyền nào đó.
Đúng. Laplacian. Bây giờ mình nói một chút về random motion nha. Random motion á, thì bạn tưởng tượng là có một cái hạt particle ở đây nha, xong nó sẽ jiggle around, nó sẽ tự nó di chuyển, và những cái đó nó là diffusion như là bạn nói, đúng không? Nó sẽ di chuyển ra dần dần. Để bây giờ mình làm cái simulation này lại. Ok, đúng không? Nó sẽ khuếch tán ra dần dần. Ok, về mặt toán học thì Brownian motion, những cái particle mà được biểu diễn bởi Brownian motion thì cái density của nó sẽ nó sẽ related, nó sẽ liên quan tới lại cái toán tử Laplace. Ok.
Yeah.
Thì ok, để mình viết ra. Ok. Ok, nếu mà em có một cái Brownian motion. Ok, mà particle của em, cái phân tử của em nó hoạt động giống như là Brownian motion. Ok, thì trong một cái miền, sau một thời gian nó sẽ đi vòng vòng, em không biết đi đâu, nhưng mà em có thể biết được là cái density của nó sẽ như thế nào. Thì cái density, gọi nó là rho đi, density nó sẽ thỏa mãn phương trình heat equation, phương trình nhiệt. Ok, thì đây là lúc mà toán tử Laplace à, sẽ hiện ra. Em có thể hiểu là những cái phân tử nó rung, nó jiggle ra như vậy, thì nghĩa là nó làm một cái việc. Nếu mà em học về gần đây thì có những cái buzzword gọi là smoothing. Ok, các bạn nào ở đây có dùng Photoshop không? Nếu mà các bạn dùng Photoshop thì nó có một cái chức năng gọi là Gaussian blur. Thì cái Gaussian blur này á, nó cũng giống như là cái việc mà cái cái density này nó làm cho cái hình ảnh của em nó, nó smooth ra, nó mờ đi, nó giống vậy.
Ủa, thế còn ở đây cái DU với DV nó nghĩa là cái gì vậy á?
Những cái này chỉ là những cái constant thôi.
Chị- Cảm ơn.
Nếu mà ok, cái bài này nếu mà em, nó chỉ ra như thế này nếu mà em chọn đúng constant. Ok, đây bây giờ anh sẽ cho em coi cái này, du dv mình có thể thay đổi được ở đây. Ok, bây giờ anh đổi du, nó sẽ thay đổi. Du hơn có nghĩa là u nó khuếch tán nhanh hơn. Ok, nếu mà u khuếch tán rất nhanh thì nó sẽ chiếm trọn cả miền. Ok, tune back lại. Đó, những cái này thì em chơi vòng vòng với lại những cái constant này thì em sẽ thấy được nhiều pattern khác nhau.
Vậy cái chất U ở đây là chất màu vàng ha, là chứ
Ờ,
sao mà anh
đúng,
tăng
đúng,
DU
đúng.
lên thì
Quên, V là chất màu vàng. Hình như là cái này là slider nhầm. Đúng rồi, V V nó phải lên, thì V nó lên thì là V nó sẽ khuếch tán nhiều hơn.
chị
Ok, các bạn còn câu hỏi nào khác không?
Em có một
Thì
câu
những cái
hỏi.
này ok rồi.
Cái phương trình hồi nãy á, thì cái Brownian motion hay là cái randomness là nó là cái hệ liên quan đến cái hệ số nào?
Randomness là cái này là tức là V là density của một chemical V, U là density của một chemical U. Thì những cái particle đó nó sẽ là hai cái Brownian motion riêng.
Ồ, tức là cái nó là Brownian motion nhưng mà khi mà accumulate lại thì nó lại follow một cái constant times cái Laplacian cái change.
Cái này cái này thì Trung có thể hiểu được là cái này là density của một cái stochastic process X, đúng không? Cái này density của một cái stochastic process Y. Thì cái này được được drive bởi một cái Brownian motion có một cái hệ số du thôi. Còn cái này được drive bởi một cái Brownian motion với một hệ số dv. Tức là cái speed của propagating của thằng U với lại thằng V nó sẽ là du và dv. Tốc độ khuếch tán. Không biết có address được được cái mà Trung nói không?
Chắc em phải suy nghĩ thêm. Hay là tại vì nó có rất là nhiều particles. Cái này là chỉ là một, cái này là mô tả nó model có một cái particle thôi anh.
Thì nhiều particle behave the same way. Nhiều
Ok,
particle
dạ,
nhiều particle behave the same way. Yeah.
ok,
Thì
dạ.
tức là mỗi cái chemical đúng không? Mỗi cái chemical, mỗi cái phân tử nó có một cái tính chất khác nhau, thì cái tính chất nó sẽ được capture bởi những cái hằng số này. Thì tốc độ gọi là phản ứng hay là cái gì đó, này anh cũng học hóa không giỏi nên là không biết. thì, thì tốc độ gì đó thì nó sẽ được capture bởi những cái thứ này.
Chắc là cái câu hỏi của em là có cái random variable nào ở trong cái equation này không, hay là mọi thứ nó vẫn
Không, cái
à
không có random variable nào, mà cái này chỉ diễn tả density thôi.
ừ. Vậy vậy cái mà previous example mà anh mention Brownian motion là để nó link với cái equation này như thế nào?
Tại vì là cái density của Brownian motion sẽ có dạng heat equation.
Ồ,
Ok.
dạ,
Thì tại vì U cũng là density, cho nên nếu mà cái process của chung á mà nó được drive bởi Brownian motion in some way á, thì cái toán tử này nó sẽ hiện diện
dạ,
cho cái density của nó. Và on top of that thì không những cái này nó move đúng không, mà nó còn phản ứng. Cái này là phản ứng hóa học. Phản ứng hóa học thì nó khác với lại spatial movement. Spatial movement được drive bởi Brownian motion, và phản ứng hóa học được drive bởi cái phương trình này, cái này. Thì hai cái process nó hoạt động gần như là cùng một lúc.
dạ. Cảm ơn anh.
Cái này thì thực ra là lúc đầu Trung bảo là mình nói talk cho các bạn học cấp 3, thì cũng run đúng không, thì không biết nên nói gì. Thì cố gắng là làm cho tuy là những cái này nhìn nó khá là phức tạp, nhưng mà cái point ở đây là vì từ những cái phức tạp này, nếu mình hiểu cái philosophy đằng sau của nó, thì nó sẽ đơn giản hơn một chút, và mình sẽ có thể tạo được những cái thứ mà nó đẹp từ những cái concept đơn giản, những concept đơn giản hoặc là phức tạp. Tại vì lúc đầu mình chỉ nói về random đúng không? Random thì nó lúc đầu tiếp cận thì nó khá là đơn giản, nhưng mà từ từ về sau mình build lên, mình dựa vào những cái phương trình nó hơi phức tạp một chút, thì nó lại ra những cái thứ mà mình không expect được. Thì đó là cái thứ mà cái thông điệp mà mình muốn gửi.
Cảm ơn anh. Có còn bạn nào có câu hỏi nữa không? Còn ai có câu hỏi nữa? Nếu như không còn thì mình có thể dừng cái buổi guest lecture thứ hai ở đây. Rất là cảm ơn anh Sơn và mọi người đã tham dự buổi hôm nay.
Ok, cảm ơn các bạn.
Cảm ơn mọi người. Chào mọi người.
Bye bye.
Chào anh.